The Mara Speech Recognition System.
Hello, I'm here today to demonstrate a real-time isolated word speech recognition system we've been developing over the past few years here at Berkeley. The system is designed to test the effects of different user interfaces when speech recognition is used, and also to help aid real-time speech recognition algorithm development. The heart of the system is a single multi-bus board that was also developed here. The board contains two special purpose chips. One, a filter bank chip that performs spectral analysis, and the other, a time warp chip to perform the pattern matching. The board also contains an Intel 8186 microprocessor, 480 kbytes of memory, and various I/O buffers to plug into the multibus and to plug into two serial external ports. The board plugs in currently to a Sun Microsystems workstation. The workstation consists of a high-resolution monitor, a keyboard, and a mouse, and of course a speech recognizer. Close. Open. Stretch.
Here you see the basic window management functions being performed by a combination of speech and mouse movements.
Hide. Stretch. Move.
Speech commands have replaced the normal mouse-driven menu.
Read mail.
In this window, a spoken word is associated with an arbitrary string of characters.
1.
This string is sent to the window when the word is spoken.
2. Preserve letter. 1. 3. Quit mail.
In order to provide feedback to the user, the recognizer has its own window on the screen. This window shows the number of words loaded and the number of templates for those words. It also shows the peak inward energy, a long-term average of that energy, and background noise estimate. With this information, the user can set the proper gain in his preamp. Finally, each spoken word causes an ordered list of candidate recognized words and scores to be presented to the user. One of the most common uses for these workstations is the development of new programs. In order to aid this development, we have written a speech-driven C program editor using the Emacs macro language.
Next. If argc is less than 2. Next. Next. Print usage. Expression.
To add a new variable name to be recognized, one merely types the name. The system will then ask you to speak the word. The variable can be used by merely saying its name.
Limit. Equals A to I. Expression. argv. Subscript. 1. Next. 4. I equals 1, semicolon. I is less than, limit, semicolon. I, increment. Next. Printf, expression. Double quote, comma. I, comma, I, times, I. Done. Done. Next. Int, I, comma, limit. Done. Compile.
When a new application is started, it loads its vocabulary into the recognizer. If a word has no templates on disk, the user is prompted to speak the word. A template is created and stored on disk.
Bottom. Accept. Again. Cancel. Copy. Cut. paste, undo, scroll down,
Here we see the recognizer
Scroll
being
down.
used in the Berkeley Smalltalk environment.
bottom, top, scroll down, scroll down, cut, paste, undo, copy, paste, cancel.
One of the most advantageous
Push.
uses for speech recognition is in environments where one's hands and eyes are already busy performing other tasks. A good example of this is a VLSI chip editor. Here the recognizer is being used with Kick,
Boxes.
a chip editor that was designed here a few years ago.
Cut. Cut. Select. Poly. Stretch box. Deselect. Boxes. Implant. Select. Layer. Stretch box.
The chip being designed performs 3x3 convolutions for an image processing system.
Deselect. Select. Copy. Deselect. Select. Stretch box. Stretch box. Stretch box. Stretch box.
Today we're going to see use of speech recognition system in an exploratory programming environment called Smalltalk 80. Smalltalk 80 has been the end product of 10 years of development at the Xerox Palo Alto Research Center in trying to improve programmer productivity. The basic philosophy of this research group was to throw computer cycles at the programming problem. The solution is of two flavors: the user interface and the programming style. The user interface, using a mouse, windows, scroll bars, and pop-up menus, has been popularized by the Macintosh from Apple. The programming style, so-called object-oriented, has not yet reached the commercial marketplace. Berkeley's role in this effort has been in the moving of Smalltalk into less expensive computers. David Unger, a PhD student at Berkeley, came up with a virtual machine to run Smalltalk. We called this virtual machine Berkeley Smalltalk, or BS, as we lovingly refer to it. Berkeley Smalltalk runs on the Berkeley Unix software system, which runs on top of the Sun workstation. All of those projects were funded by DARPA. The addition to the standard setup is Professor Broderson's VLSI chip on a multi-bus board which is put into the Sun workstation. Today's demonstration will have two versions. First, the traditional version, using a mouse, pop-up windows, and a scroll bar. The second, voice-trained system. Jeff Lowe, a Berkeley undergraduate, has come up with this combination of the Berkeley Smalltalk and Rodeson's speech recognition system. During the first version of the demonstration, you may see Jeff's hand leave the keyboard to use the mouse to do both the scrolling of the window or the selection of the entries in the pop-up menu. During the second version, you'll see that he can use voice instead of the hand movements. We'll probably notice that the Berkeley Smalltalk system runs fairly slowly at times on the Sun workstation. Another research effort is to build a custom VLSI chip to run the Smalltalk system at least an order of magnitude faster than the one you'll see today. So here's Jeff Lowe to do the demonstration.
Here we see the standard Smalltalk interface. Commands are entered by selecting items in a pop-up window. Here the speech recognizer is being trained.
Scroll up. Scroll down. Top. Bottom. Accept. Again. Cancel. Copy. Cut. Paste. Undo. Scroll down.
Now let's edit using voice.
Bottom. Top. Scroll down. Scroll down. Cut. Paste. Undo. Copy.